Hey guys, I am alone in my apartment today, which means I can actually go ahead and record yet another video. So welcome back, because we're going to be doing some more low-level design. And for today's video, we are going to be doing a parking garage implementation. So as a kid from New York City, I'm not the best of drivers. I definitely have a lot of trouble with parallel parking. And I would have to say that, when it comes to fitting in tight spaces, I've always definitely empathized more with the parking spot than the car. I tend to prefer other people do the work there. So without further ado, let's go ahead and get into this challenge. There are a ton of different functional requirements for a problem like this, so I'll name the ones that I'm going off of, but maybe, in an actual interview, they might extend this problem quite a bit. And so it's possible that I'm not going to cover everything, but I'll do my best to, address different aspects of this problem where I can. So let's go ahead and get into it. Okay, starting off, a parking garage. So we all know what it is. Basically, that's where you go when you have a car and you need to go ahead and store it somewhere while you go out and do your thing. But generally speaking, what are the functional requirements of this problem? Basically, we want to design some sort of parking lot that has three major requirements. We want to be able to enter the lot as a car and basically receive a spot to take at the moment of entry, right? So we would get a ticket from the entry and it would tell us which spot to take. Similarly, we want to be able to exit a lot. And then the last kind of piece of this puzzle is also just, if you're driving around and are considering entering the lot, to be able to see how many available spots there are of each type. So I'm going to assume there are three types of spots. We can call those big, medium, and small. And for now, just to simplify things, I'm going to assume that only big vehicles can fit in big spots, medium in medium spots, and small in small spots. But this doesn't really complicate the problem too much. And again, different interviewers might have different requirements here. Perhaps some would say like, oh, a small vehicle could go in a big spot, but ideally we should prioritize the small spots first. So that could complicate things a little bit, but for now, I'm not really going to consider that. Okay, so let's think about the actual parking garage itself. So we know that we want our parking garage to probably be an interface. The reason for that being that amongst parking garages, we've kind of standardized the way that a user might interact with it, right? They're just going up to the entry and exit point and asking for a ticket or giving them back their ticket or seeing how many available spots there are. But within that actual interface that a user might use to interact with the parking garage, we don't actually know how the implementation is going to happen under the hood. So it's important that we kind of have this standardized interfaces so that users can interact with it in kind of a normalized way. But under the hood, we may actually determine the way that parking spots are given out in multiple different types of implementations. And as a result, interfaces are probably the way to go here. So if we are actually going to have an interface as our parking garage, what are those three main methods going to look like that we have to be implementing? Well, the first one is going to be to actually enter the garage. That is going to take in something like a car size, an entry number, because it's possible that a parking garage might have multiple entrances and exits, and then also a license plate number. And basically what this is going to mean is that, a car with a given license plate is coming in through a certain entry number, and that car has a given size, and all our parking garage is going to do is going to return the name of the actual spot that it is that they're going to be taking. Similarly, we also have this concept of exiting, and that's when a car is leaving the parking garage. It's going to give back its ticket, which has basically its license plate number and also its car size and entry number, and then we can go ahead and basically vacate that spot again and say this is now open for future cars to take. The last piece of this puzzle is actually getting the number of spots. We don't need any methods for this parameter because more or less all that's going to happen is we're just going to display a map of, car size medium, 100 spots, car size small, 10 spots. So it's just going to tell you how many available spots there are for each size. Do we actually need any other classes? Well, to get started, we probably don't need a vehicle class. The reason for this being that, in our case, vehicles actually aren't holding any stateful information. The vehicle itself is not really part of the parking garage, but what really is actually the parking spot, because we need to know if a given parking spot is occupied or it's not, and also certain aspects about the parking spot, such as its distance to each entry or exit. And so let's go ahead and take a look at a parking spot class. So here are some of the actual fields that might be really useful for us. As you can see, we have this parking spot, and then it's going to come with a size, so I'm assuming a size is part of this size enum, which could be something like small, medium, or big. It's going to have a name, and that name is going to come in handy if we ever need to use something like a hash map from parking spot names to parking spots. And then also finally, I have this concept of a list of distance to entrances. So imagine that we have, 5 entrances. This list, distance to entrances, is going to have a corresponding distance in, who knows, say meters, from this particular parking spot to every single one of those 5 entrances. So, distance to entrances at the 0th index would be basically the distance to that first entrance of the parking lot. Okay, so let's think about some possible implementations of our parking garage. Because we've said that this is an interface, there's definitely many different ways that we can go ahead and assign spots. And as a result of that, some are going to be better than others, and some are maybe going to have some algorithmic complexity trade-offs, and some are going to have some practical trade-offs. So let's think about one that would have really good algorithmic complexity. Well, a simple naive way of assigning spots would basically just to maintain queues for every single type of spot, right? So we would have a queue for the small spots, a queue for the medium spots, and a queue for the large spots. And basically, as cars come in and request spots, we just go ahead and assign the first element of that queue to them and then remove it from the queue. This is really nice because this implementation is in O of 1 time. We don't have to do any thinking about what the best spot to assign someone is, but rather we just go ahead and give them one basically randomly using something like a queue, which is effectively just saying like, what is the least recently used spot? Let's go ahead and give you that. So that works well, and it'll definitely give everyone a spot, but practically speaking, that's not that great. The reasoning being that these spots are basically going to be put in the queue randomly. And what if I'm entering through a parking lot entrance that is really close to a few spots? Wouldn't it be better if I assigned a user a spot that was actually closer to that entrance? And if this is kind of the case that you want, what we can instead do is use a priority queue data structure. So this is really useful in the sense that using a priority queue, or basically a min heap under the hood, is going to allow us to quickly find the parking spot object that has the least distance to that entrance. Now the issue here is that I've mentioned that there are multiple possible entrances in our parking garage, and each entrance is also going to have a corresponding exit, but let's not worry about that for the moment. And as a result, we're going to have to maintain many different queues, or many different priority queues rather, showing the distances to each one of those entrances. And so every single time that a car is entering from a given entrance, we have to pull up the correct priority queue, both for the corresponding size of the car and also the corresponding entrance. And once we go ahead and figure out which spot is being assigned to that car, we then have to remove that parking spot not only from the priority queue for that entrance, but also from the priority queue for all of the other entrances. And for us to do that in a relatively efficient way, we have to maintain a hash map from a parking spot name to basically its location in all of those priority queues so that we can relatively quickly remove that node from all of them. Another possibility that I cover on this slide, though I won't touch upon it too much, is that we can actually kind of shard up our parking lot. So if we have many entrances throughout the parking lot, and they're all in different zones per se, we could basically make it so that only a single entrance is allowed to assign spots from a single zone. So let's say I have this massive parking lot, it's a big rectangle, and I have an entrance on the left side and an entrance on the right side. I could split my parking lot down in the middle and only assign spots from the left side to one entrance and spots from the right side from the other entrance. And they won't basically go ahead and take spots from each other's zone. The final possibility, or the final thing to think about, is depending on how this parking lot is implemented, and if it's possible that multiple entrances can be assigning the same spots, we may actually have to think about doing some sort of locking or dealing with thread-safe programming, in the sense that we don't want the same spot to be assigned twice. There could be a race condition there, where if 2 cars arrive at basically the same time, they may end up being assigned the same spot, and that can't happen. So it's possible that you would have to actually do some locking here, but for the sake of this problem, we're not really focusing as much on the concurrent programming aspect of things, and more so on the object-oriented design. Okay, so I'm actually going to go ahead and now implement this concept of a priority queue parking lot, right, where we're trying to assign the closest spot to each entrance that's still available. And this is going to get a little bit confusing. I do use some pseudocode because the reality is coding this would actually not be that easy, but I'm going to try and do my best to explain it in a way that makes sense to you all. So basically we're going to have the following. So let's imagine we have our priority queue parking lot, and the constructor is basically going to take in a list of parking spot objects and also a number of entrances, right? So the first thing that we have is this concept of a car map. For now, I'm going to say that car map is just an internal field, and it's going to maintain a mapping from basically car license plate number to the actual parking spot object that that car is located in. But then furthermore, we want to make sure that for every single parking spot in our garage, and also for all of the number of entrances, we want to be basically putting that parking spot in the corresponding queue or priority queue that belongs to it. So firstly, what we're going to do is go ahead and add it to the priority queue. And then also once we have the index in that priority queue, because keep in mind that priority queues are implemented as min heaps, which are basically just arrays under the hood, we need to know the actual index of the array that that parking spot was placed in. The reasoning for this being that we're going to constantly be removing things from multiple queues. And when we're removing them from the priority queues, they're not necessarily at the root node of that heap. And so in order to still maintain O of log n complexity as we're removing nodes from the priority queue, we have to actually know exactly where they're located in the priority queue before removing them. Otherwise, we would have to do a linear find for that parking spot in the priority queue, and then we would ruin our time complexity. So it's very important that we keep some data structure that allows us to see where these parking spot nodes are in every single queue in terms of their actual index. So that's what the parking spot hash map does. It goes ahead and says, okay, for a given parking spot name and also the actual entrance, where is that location in the priority queue? And then additionally, we're also just going to go ahead and add all of these parking spots to the proper priority queues, and also making sure to put them in the right size queue, right? So for example, if it's a small parking spot, we need to make sure to put it in the small parking queue. Okay, and we're doing that, of course, based on the distance from entrance I. If you recall from the parking spot class, we have the distances to each entry, and so we're basically using that field to assemble those queues. Phew, so I know that's a lot, but we're still going. Let's go ahead and get through this. The easy method to implement is actually getting the number of spots. So basically, we only really need to consider, one set of queues here. So basically, looking at this from entrance 0, we go through all of those priority queues for small, medium, and big cars. We loop through those, and then we create a dictionary, which basically says, dictionary of the small key has 100 spots, dictionary of the medium key has 50 spots, etc., etc. So easy enough for getting the number of spots. The more complicated part is the entry and the exit methods, and I'm going to go through those now. Okay, so let's imagine we're calling enter, and we have basically the size of the incoming car, we have the entry number that we're going through, and we also have the license plate number of the incoming car. So the first thing that we're going to do is figure out the proper priority queue to go ahead and check in order to remove an element from that priority queue. So that priority queue is going to be the one corresponding to the entry number that we're coming through, also with the proper car size. Then we're going to go ahead and find the top element of that priority queue, which is the spot that we know that we're going to be taking. So we can do that by peeking at our priority queue. We also get the name of that spot so that we can use it in our actual hash maps itself later when we're removing that element from all the priority queues. We then go ahead and use the car map, because we know that our car map is basically mapping license plate numbers to the spot that they're in so that we can vacate it later. And so we're going to set that element in the car map. And then finally, for every single priority queue, we have to now remove this parking spot. And so we go through the priority queues basically and go and say, okay, find the element, or basically find the index of the array in the priority queue that this parking spot is located at, and we have that from our parking spot hash map. We go ahead and do that, remove those all from the priority queue, so those are all going to be logarithmic time complexity operations, and once we've removed that parking spot from every single priority queue for each entrance, we can go ahead and move on to our actual exit method. Okay, so now the exit method is pretty much symmetrical to the entry method, but instead of this time removing that parking spot from all the priority queues, now we have to go ahead and add it back to all of the priority queues, which is pretty annoying, but it's a similar thing. So the first thing we do is we know that we have a given license plate number, and as a result, we can quickly go into the car map to find out which spot it was that that car was occupying. Then we can go through all of the priority queues for each entrance and basically say, we're going to figure out the index number. We're basically going to add this spot back into all of the priority queues, figure out the index in the array of the priority queue that they were added to, and put that back in our hash map in the event that we have to remove this spot from all the priority queues later. Okay, well, I hope that makes sense, guys. I understand that this is kind of abstract as far as algorithms go. But again, there are many, many different types of possible implementations that you can do, and frankly, kind of the concept of having multiple entrances and exits with priority queues like that is not a simple thing, and I don't think anyone would expect you to code that out in an interview. But the general gist of this video is, thinking about what parts of the parking garage actually need to store state and which don't. And in this case, you don't need an entry class, you don't need an exit class, you don't need vehicle classes. Just having an implementation of a parking garage for the logic surrounding which spot to give, as well as actually having implementations for parking spot objects in order to store the state of whether or not they're occupied, should be sufficient for this problem. Alrighty, everyone, I hope you all enjoyed. Shout out Xavier Zhao, who has asked me to make this video, and I'm coming through on my promise, buddy. But do expect me to sell out in the near future as I continue to run out of video ideas, but for now, let's keep busting through low-level design.